Good morning, students. I am Dr. Neeraj Gupta. Now let's start with let's continue with the chapter of stability that we have discussed in the last module. Now in that case, we have seen that we have analyzed the denominator of the system and find the location of the roots, and from that by this denominator we can easily tell about the what type of system it is. Now let us take a small example. Let us suppose that we have two roots of the denominator that is a and the b, which are on the left side of the plane, and then we expand it. After expanding, we get this equation, that we get this polynomial. From this we can see that all the coefficients of the polynomial are positive in this case. However, if we take another case in which one of the roots is on the right side of the plane, that is one of the roots is on the right side of the plane, then in that very case, when we expand it, we get that we get one sign, that is negative sign here. So for the system, for any system to be stable, there is no sign change, that is all the coefficients should be positive in this case, and there should be no sign change. Now let us take the case where one coefficient is that is where one, let us suppose a term is missing in that. Let us suppose that we have this equation, and let us suppose in that case one term is missing, this term is missing. It means that the missing term means that there should be a plus b equals to 0. So one term should be negative in that, that is either we have that is minus a, or we have minus b. It means that one of the root is on the right hand of the plane, and as a result it is unstable. So the necessary condition for the system this to be stable, that there is no sign change in the denominator, and also there is no sign change in the denominator, and also that we have observed here, that is there is no missing term, because if some missing term is there, then it means that some term is negative, that's why missing term is there. So if there is any missing term in denominator, then we can say that that is an unstable system. So from that we can analyze the system. Now we discuss this Routh-Hurwitz criteria in detail. Now in this section we learn a method that yields stability information without the need to solve for the closed loop system poles. That is, there is no need to solve the poles of the system, that is from the equation only, from the denominator only, we can simply tell about the nature of this system. Now using this method we can tell how many closed loop poles are in the left half plane, in the right half plane, and on the JW axis. Okay, so one point is emphasized here, that it tell about that how many poles are there, but not where. It doesn't tell about the whereabout of that poles, but how many poles are there, whether it is on right hand side or the left hand side, but it doesn't tell about what's the exact location. So we can find the number of the poles in each section of the S-plane, but we cannot find their coordinates, and this method is called the Routh-Hurwitz criteria for the stability and it was developed by Routh in 1905. Okay. Now this method requires the two steps. That is, it requires the two steps, that is, generate a data table called the Routh table. So data table is generated, which is known as the Routh table, and then we interpret the Routh table to tell how many closed loop system poles are in the left half plane, the right half plane, and on the JW axis. So that interpretation can be done. Now one more point is that you wonder that why to study the Routh Hurwitz criteria when the modern calculators and computers are there. These can tell the exact location of the system poles. So actually the power of this method lies in, that is, the power of this method lies in the design. Power of this method actually lies in the design, okay, rather than the analysis. Now let us suppose that we have an unknown parameter in the denominator. Let us suppose some unknown parameter is there in the denominator. Okay, and that is in that polynomial of the denominator, and it is difficult to determine via the calculator the range of this parameter to yield the stability. So we have to rely on the trial and error to this stability question. Now we can see later in this chapter that how this criteria can yield a closed form expression for the range of the unknown parameters. Now come with the generating the basic Routh table, that how the basic Routh table can be generated. Now let us since we are interested in the poles only, so we focus our attention only to the denominator rather than going anywhere. So our focus should be the denominator only. Now this table is actually, first one is the initial layout of the Routh table, and this is the completed Routh table. Now first we begin by labeling the rows with powers of s from the highest power of the denominator of the closed loop transfer function to S0. That is, first we label S4, S3, S2, S1 and S0. That is, we label the rows with the power of s from the highest power of the denominator of the closed loop transfer function to the minimum. Now next we start with the coefficients of highest power of coefficients of the highest power of s in the denominator, okay, and list horizontally in the first row every other coefficients. Like let us suppose that it is S4, so A4, then we have the A2 and A0. In the first we have A4, A2 and A0 skipping in between. Second is A3, A1 and 0, that is nothing is there, so skipping in between. Okay, so in the second row, the horizontally starting with the next highest power of the s, every coefficient that was skipped in the first row. So in the first row we start with the coefficient of S4, then S2, then this one, that is S0, and in the second we start with the S3, that is A3, then coefficient of S1 is equals to A1 and 0, and the remaining entries are filled as we will discuss here. Now remaining entries are filled like that. That is, each entry is actually a negative determinant of the entries. each entry, let us suppose this one is the negative determinant of entries in the previous two rows divided by the entry in the first column divided by the entry in the first column directly above the calculated row. That is, you can say A4, A3, A2, A1 divided by A3. So each entry is the negative determinant of entries in the previous rows divided by entry in the first column directly above that row. That is, to that row you will see that if that is A4, A3, A4, A3, then we have A2, A1, then we have A2, A1 divided by A3. Okay, let us suppose that it is B1. Now second one is A4, A3, A4, A3, then A0, then we have A0, 0, then we have A0, 0 divided by A3, this one. So it is, let us suppose that it is B2. Then we have A4, A3, since no entry is there, then 0, 0 divided by A3, this one. Okay. Now similar is the case with the other rows also. The left hand column of the determinant is always the first column of the previous two rows, and the right hand column is the elements of the column above and to the right. Now this table is completed when all the rows are completed down up to S0. That is, this one you can we can see that it is A3B1. That is, we have A3, then we have B1. Okay, A3B1. Then we have A1B2. Then we have A1B2 divided by this B1. Similar is the case with the other elements of the row also, and here also we can you can see it is B1 C1, B1 C1, then we have B2 0, then we have B2 0, then it should be C1 divided by C1, so it is D1. So in this way Routh table is completed. Now let us take an example. We have to calculate the Routh table in this case. Now in this case it is given, that is the system is given, it is a unity feedback system. So first step is to find the equivalent closed loop system, because we want to test the denominator of this function, not the given forward transfer function. So we find the equivalent closed loop system. So this is the equivalent closed loop system in this case. Okay, now that can be obtained by using the feedback formula that we have already discussed. Now the Routh criteria will be applied to the denominator. First what we do, first we label the rows with the power of S from S3, that is, it is the highest power, down to S0 in the vertical column, that is S3, S2, then S1 and then S0. Okay. Next, form the first row of the table using the coefficients of the denominator of the closed loop transfer function. Here we have S3, the coefficient is 1, then we have S, the coefficient is 31, and then we have nothing is there, so it is 0. Second is we get the coefficient of that is, we have to write the coefficient of S square, so it is 10. Then we have to write the coefficient of this term S, that is skipping 1, so 103 and then 0. Then whatever we have discussed in the previous in this sometime back, we that is 1 divided by 1, that is 1 31, and okay, we have to discuss this 1030. Now again, So what we have done, we start with the coefficients of the highest power and skip every other power of s. Now from the second row with the coefficients of the denominator skipped in the previous step, subsequent rows are formed. Also, for convenience, any row of the Routh table can be multiplied by a positive constant without changing the values of the rows. That is, any row can be multiplied by a positive constant without changing the values of the rows, and this can be proved by examining the expression for entries and verifying that any multiplicative constant from the previous row cancels out. So in the second row, you will see that in the second row we have 10. In the second row it was 10 and then 1 0 3 0. Then we multiply it by 1 by 10. When we multiply it 1 by 10, we get here 1 and 1 0 3. Okay. So also, however, we can see later in the section that care must be taken not to multiply the row with the negative constant. It is only the positive constant. Here we have multiplied it by 1 by 10 and we get this 1 here and 103 and 0. So it is nothing. Now, so in this way we get the Routh table, that is from here we get 1 1, then 31, 103 divided by 1 which is equals to 72. Then again we have 1 1, then we have 1, sorry, it should be 1. It is wrongly displayed here, so it should be 1. Now we have, then again we have this 1 1, okay, and it is again here it is also, then we have 0 0, then after that 1 1 and 0 0. Again we have 1 divided by 1 minus 72, minus 72. Then we have 103 and 0, 103 and 0 divided by this 72. In this way we form the complete Routh table. Now we interpret this Routh table. Now we interpret the basic Routh table. Now Routh-Hurwitz criteria declares that the number of the roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. That is, the number of the roots of the polynomial that is in the right half plane is equal to the number of the sign changes in the first column. Okay. Now this basic Routh table applies to the system with the poles on the left and the right half planes. However, the system with imaginary poles and the kind of the Routh table that results will be we discuss next. Now if the closed loop transfer function has all the poles on the left half of the S plane, the system is stable, and the system, if the system is stable, if there are no sign changes in the first, and if there is no sign changes in the first column of the Routh table, that is, for the system to be stable, all the poles must be on the left hand side and there should be no sign changes as we have discussed initially. For example, we see that table has 2 sign changes in the first column. Like you will see that from here we see it is minus 72. So from positive to negative, then from negative to positive. So there are that is two sign changes in the first column. You see, the first sign change occurs from 1 in S2 row to minus 72 in S1 row, and the second changes from minus 71 of S1 row to 103 in S0 row. The system is unstable since the two poles exist on the right half plane. So from seeing that table only and seeing the change of the sign in the table, we can interpret that there are the two sign changes, and as a result two poles exist in the right half plane in this case. Okay, so we have the two poles on the right hand plane. In this way we can draw the interpretation for the other cases also. Now this is a small problem for you that you have to do at your own end. So you have to make a Routh table and tell how many roots of the following polynomial are in the right half plane and in the left half plane. You can draw the Routh table and interpret the result from that. Also one more point is that the coefficient should be, that is no term should be missing in this case. That is, you have to see that the no term should be missing in this case. If the term is missing, then outrightly you can say that system is unstable. Okay, now so in this way, by using the Routh criteria, you can tell about the this system, that what type of a system is it. In the next module we can discuss about the special cases. That is, there are certain special cases in that case, in this also, that how to deal with those special cases. Now in this lecture, what we have done, so we have discussed about this Routh Hurwitz criteria, the basics of that how to make a Routh table and how the analysis can be done for the simple case. That is how we have generated that table, and how we analyze that table, and how we interpret that table. That is also discussed here in this lecture. Now in the next module we will discuss about the special cases of this Routh Hurwitz criteria. That is, there are two special cases, that the Routh table sometimes have a 0 only in the first column of the row, and sometimes it have an entire row that consists of 0. That in the next module we can discuss that how we deal with those cases.